Welcome to ChemVault Advanced Chemistry Series. In this module, we are going to build a rigorous exam-ready understanding of polymers, from the very definition of a macromolecule all the way through polymerization, kinetics, molecular weight analysis, and industrial application. This lecture is designed for postgraduate learners. If you're preparing for GATE, CSIR NET, or a university level course, in polymer chemistry, this is pitched exactly at that level. Let's get started. Before we dive in, let's see the roadmap. By the end of the session, you'll be able to do six things. 1. Classify polymers by origin, structures, and mechanism of polymerization. 2. Drive and apply the kinetics of a chain growth polymerization, both radical and ionic. 3. Apply the Carothers equation to solve step growth polymerization problems, which is a favorite in GATE numericals. 4. Compute number average and weight average molecular weights and interpret dispersity. 5. Connect glass transition temperature and crystallinity to real bulk properties. And 6. Read and interpret characterization data from GPC, d.sc, TGA, and XRD. Keep these six pillars in mind. Everything we cover today builds towards them. Let's start from the first principles. The word polymer comes from Greek poly meaning many and meros meaning parts. So a polymer is simply a very high molar mass macromolecule built by joining together many small repeating units called monomers through covalent bonds. A few definitions you must know. Cold. The monomer is the small reactive molecule you start with. The repeat unit is the smallest structural fragment that repeats along the backbone. And note, the repeat unit is not always identical to the monomers, especially in condensation polymers. The degree of polymerization denoted little n or dp is simple, the number of repeat units in a chain, calculated as the total molecular weight of the polymer divided by molecular weight of one repeat unit. And functionality, the number of reactive sites on a monomer is critical. A functionality of 2 gives you linear or branch chain, but a functionality of 3 or more introduces cross links and networks. Structure, we'll come back to that distinction very soon. Look at the example on the right. Polythene. The monomer is ethylene, CH2 equals CH2 with a molar mass of 28 grams per mole. If a polymer chain has a molecular weight of 280,000 grams per mole, the degree of polymerization is 280,000 divided by 28, which gives us 10,000. Repeat units in that single cell, simple division. But this is the calculation GATE loves to test. Classification by origin. Now let's classify polymer, and there are multiple ways to slice this. So pay attention to which lens we are using each time. First, by origin. Natural polymers occur in living system. Cellulose, starch, natural rubber, which is cis-1,4 polyisoprene, proteins and even DNA. Synthetic polymers are engineered in the lab or plant. Polythene, nylon, PVC, polystyrene, and semi-synthetic polymers are natural polymers that have been chemically modified. Cellulose acetate and vulcanized rubber are the classic examples. Second, we can classify by what makes up the backbone itself, organic or homogeneous. Polymers have all carbon backbone. Think polythene, polyethylene, PVC, polystyrene. Heterochain polymers have oxygen, nitrogen, or sulfur built into the backbone. Polyesters and polyamides, like nylon, fall here. And inorganic polymers have a backbone built from elements like silicon or phosphorus. Silicon and their silicon oxygen backbones are the most industrially important examples. Classification by chain. The third classification, lens is chain architecture, and this is one of the most exam relevant classification because it directly predicts material behavior. Linear chains are simple, unbranched sequence. Think of a strand of spaghetti. Branched chains have side chains coming off the main backbone. Cross-linked structures have occasional covalent bridges connecting different chains and network. A three-dimensional structure are densely cross-linked in all directions. Here is the key exam insight. This architecture is directly governed by functionality of the monomer that we discussed earlier. A functionality of 2 gives you a linear or branch chain. These remain thermoplastic, meaning they can be melted and reshaped, and they often soluble in appropriate solvents. But once functionality reaches 3 or highest, you start forming crosslinks and eventually a full three-dimensional network. And that's exactly how thermosetting polymers like phenolformaldehyde resin epoxy are formed. Once that network forms, material becomes insoluble, infusible. It simply cannot be melted or dissolved. Again, because you have to break covalent bonds to do so, not just overcome intermolecular forces. Mechanism, chain growth versus step growth. Now, the third and arguably most important classification by mechanism. There is where polymer chemistry really splits into two distinctions, kinetic worlds, and understanding this distinction will unlock everything that follows. Chain growth or addition. Polymerization works like this. An initiator creates one reactive center and monomer adds one at a time rapidly to that single growing chain end. The result, high molecular weight polymers forms almost immediately. Even at low overall conversion, you either have long chains or you have unreacted monomers. There's very little in between. No small molecule is eliminated. So the polymer's molecular formula is simply n times the monomer. Polyethylene, PVC, PMMA, polystyrene, these are all addition polymers. Now comes step growth or condensation polymerization is fundamentally different. Any two species present monomers, dimers, or growing oligomers can react with each other. There is no initiator required. It proceeds purely through functional group chemistry, like an OH reacting with a COOH. Molecular weight builds up slowly and only shoots up right at very end of the reaction at very high conversion. And critically, a small molecule, water, HCl, or methanol, is usually eliminated as a byproduct. Nylon 66, PET, polycarbonate, these are all condensation polymers. Keep this contrast firmly in mind because the kinetics we cover next are built entirely on this distinction. Free radical addition polymerization. Let's now drive the kinetics of chain growth polymerization, starting with the free radical mechanism. This has three distinct steps, and you need to know each one's role. Step 1, Initiator. An initiator, commonly benzoyl peroxide or AIBN, undergoes homolytic cleavage to generate two radicals with rate constant Kd, K/D. That radical then adds to a monomer molecule to generate the first chain carrying radical with rate constant K is I. Step 2, propagation. This growing radical adds monomer after monomer extremely rapidly with rate constant Kp. And a key simplifying assumption here is that K/P is treated as independent of chain length, which makes the kinetics tractable. Step 3, termination. The chain growth stops when two radical meets. This can happen by combination. Here's two, where two chains join to form one longer chain, or by disproportionation, where a hydrogen atom transfers from one chain to the other, producing two dead chains, one with a double bond. Termination happens with rate constant Kt. Putting this together with steady state approximation, where the rate of radical generation equals the rate of radical destruction, we get the rate law shown here. Rp equals to K/P times monomers concentration times the square root of F K/D initiator concentration over Kt. In simple terms, the rate of polymerization is proportional to monomer concentration and to the square root of initiator concentration. The half power dependence on initiator concentration is a hallmark result. Memorize it because it appears again and again in exam questions. Slide 8, Ionic polymerization and living chains. So now we are on ionic polymerization and living chains. Free radicals are the only way to run chain growth polymerization. Ionic mechanisms are equally important and they behave quite differently. In cationic polymerization, we use a Lewis acid catalyst paired with a co-catalyst, commonly boron trifluoride, with a trace of water, and the propagation species is a carbocation. This mechanism is favored by monomers with electron donating substituent, isobutylene being the textbook example. One limitation, chain transfers to monomer is common, which makes it genuinely difficult to reach very high molecular weight. This way, an ionic polymerization uses catalysts like alkyl lithium or sodium amide. And here the propagating species is carbon ion. This is favored by monomers with electron withdrawing groups. Styrene, meth acrylates, and dienes are classical substrate, and here's what makes anionic polymerization special. Termination is often completely absent. Once you run out of the monomer, the chain ends and simply sits there, still reacting. This is called a living polymer. Why does living polymerization matter so much? Because without chain transfer or termination reaction competing with propagation, you get a very narrow molecular weight distribution, a dispersity close to 1, and predictable molecular weight calculated simply from the monomer to initiator ratio times conversion times the monomer molar mass. And because the chain ends stays alive, you can add a second monomer afterward and grow a well-defined block copolymer. This is the foundation of modern controlled polymer synthesis. So now we are on step growth, polymerization, and the Carothers equations. Now let's turn to step growth kinetics, and this is where the Carothers equation comes in. Arguably, the single most exam tested equation in all of the polymer chemistry. First, a definition: the extent of reactions P is simple, the fraction of functional group that have reacted to a given time. The Carothers equation relates this differently to the average degree of polymerization, x bar n equals 1 divided by 1 minus p. Let's work through the numbers because this is where the real insight lives. At p equals 0.98, that's 98% conversion. X bar n equals 1 over 0.02, which is 50. Now push conversion to 99.5%. P equals 0.995 and X bars n jumps to 200. Notice how dramatically the degree of polymerization increases for a relatively small increase in conversion. Near completion. This tells us something profound. To get high molecular weight polymer via step growth, the reaction must be driven to extremely high conversion, well above 99%. This is exactly why step growth polymerization requires careful control of reaction times, removal of byproducts like water, and precise stoichiometry. Speaking of stoichiometry, if you use a slight excess of one monomer defined by the ratio R equals moles of A over moles of B, the modified the modified Carothers equation becomes x bar n equals 1 plus R divided by 1 plus R minus 2 Rp. Even a small stoichiometric imbalance places a hard ceiling on the maximum achievable molecular weight. This is precisely how manufacturers control the molecular weight of nylon and polyester in industrial production, often deliberately adding a small excess of one monomer to cap the chain length. The table shows three industrially vital condensation polymers: nylon 6,6 from hexamethylene and adipic acid, releasing water; PET from ethylene glycol and terephthalic acid, also releasing water; and polycarbonate from bisphenol A and phosgene, releasing HCl. Notice the pattern. Step growth polymers are built through functional group condensation, always releasing a small molecule. Copolymers sequence and architecture. So far we have discussed homopolymers built from a single repeating monomers. But most commercially important materials are actually copolymers built from two or more different monomers, and the sequence in which they are arranged matters enormously. Random copolymers have no regular patterns. The two monomers add according to their relative reactivity, giving an essentially statistical sequence. Alternating copolymers show strict ABA AB alternations. This happens when the reactivity ratios R1 and R2 are both close to zero, meaning each radical strongly prefers to react with other monomers rather than its own type. Styrene malic anhydride is a classical alternating system. Block copolymers have long continuous segments of each monomer joined end to end, and these are typically made using living polymerization, exactly the technique we discussed on previous slide. Graft polymers have a homopolymer backbone with side chain made of second different monomer. The governing parameters here are reactivity ratios R1 equal K slash 1 1 over K 1 2 and R2 equals K 2 2 over K 2 1 from the Mayo-Lewis copolymerization equation. If both R1 and R2 are greater than 1, each radical prefers adding its own monomer, giving blocky sequence. If both are less than 1, cross polymerization is favored, pushing towards alternation. Industrially, this matters enormously. SBR, styrene butadiene rubber, a random copolymer, is what your tires are made from. ABS, acryl acrylonitrile butadiene styrene, a graft copolymer, gives you the tough plastic housing in automotive and appliance parts, and EVA ethylene vinyl acetate shows up in the forms and adhesives. Now let's talk about molecular weight, averages and dispersity. Unlike small monomers, unlike small molecules, polymers are never made of chains that are all exactly the same length. Every real polymer exactly every real polymer sample is a distribution of chain length. So we need statistical measures to describe that distributions, and this slide covers the three you absolutely must know. Number, average molecular weight Mn is calculated by summing the number of chains at each molecular weight times the molecular weight that molecular weight divided by the total number of chains. This is essentially a simple average because it counts each chain equally. It it's quite sensitive to the presence of small chains. It's typically measured through qualitative property methods or end group analysis. Weight, average molecular weight MW. Weight each chain by its own mass. So summing number times molecular weight squared divided by number times molecular weight, because larger chains contribute more weight. MW is more sensitive to the presence of large chain, and it's measured by light scattering techniques. Since MW always weighs the bigger chain more heavily, MW is always greater than or equal to Mn, and the ratio dispersity or D tells us how broad the distribution is. A perfectly uniform monodisperse polymer has D equals to exactly 1. Any real polymer will have D greater than 1. Let's work through the numbers. Say we have 2 moles of chains at molecular weight 10,000 and 1 mole of chains at 40,000. Mn works out to 20,000, a straightforward number, average, but MW comes out to 26,667, noticeably higher because it's weighed toward that larger 40,000 population. Dividing gives us a dispersity of 1.33, moderately broad. Practice this calculation until it's second nature. It's a guaranteed numerical question type. Kinetic chain length and the Mark-Hofken equation. Two more essential relationships for molecular characterization. First, kinetic chain length denoted nu. This is defined as the rate propagation. First, kinetic chain length denoted nu. This is defined as the rate of propagation divided by the rate of termination, and it works out to Kp times monomer concentration divided by 2 times the square root of f kd kt and initiator concentration. Notice the proportionalities kinetic chain length increases with monomer concentration but decrease with the square root of initiator concentration. This connects directly to the degree of polymerization. dp equals nu if termination occurs by disproportionation or dp equals 2 nu if it occurs by combination. Since a combination joins two growing chains into one, the practical takeaway, if you want longer chain, is a free radical polymerization. Use less initiator, not more. Second, the Mark-Hofking equation, intrinsic viscosity equals K times. Viscosity average molecular weight raised to the power A. Here K and A are empirical constants specific to the polymer solvent temperature system. The exponent typically falls between zero point 0.5 and zero point 0.8 for flexible coil chain is a good solvent and approaches 0 for rigid, compact, specific spherical particles. This equation is the theoretical basis for viscometric molecular weight determination, a simple classical technique still widely used. Finally, gel permeation chromatography or GPC, also called size exclusion chromatography, has polymer chains are separated by hydrodynamic volume as they pass through a porous column. Larger chains can't penetrate the small pores, so they travel faster and elute first by calibrating against narrow dispersity polystyrene standards. GPC gives you the complete molecular weight distribution in one experiment, directly yielding Mn, Mw, and dispersity. Next topic, glass transition and crystallinity. Let's shift now from molecular level kinetics to bulk thermal behavior, starting with one of the most important properties in all polymers science, the glass transition temperature, Tg. Look at the plot of specific volume against temperature. For a purely amorphous polymer, as we cool down, specific volume decreases smoothly, but at the glass transition temperature, there's a distinct kink, a change in slope. Above Tg, the polymer is a rubbery, flexible state with a segment chain motion active. Below Tg, that motion freezes out and the polymer becomes a rigid glass. For a semi-crystalline polymer, You additionally see a sharp, discontinuous drop in specific volume at the melting temperature Tm. This is a true first order phase transition. Unlike the second order, like last transition, what factor raise Tg? Chain stiffness, bulky or aromatic groups in the backbone, restrict rotation and raise Tg. Strong intermolecular forces like hydrogen bonding or high polarity restrict segmental motions and raise Tg. Bulky or polar side groups do the same. Higher cross link density raise the effective Tg because cross links physically restrict chain mobility, and higher molecular weight raise Tg to thousands. Though this effect plateau at high molecular weights, one practical application worth remembering: plasticizer works by the opposite mechanism. Small molecules that insert themselves between the chains, increasing free volume chain mobility and thereby lowering Tg. This is exactly how rigid PVC is transformed from the flexible material used in cables and flooring. Next topic is thermoplastic, thermosets, and elastomers. Now let's connect architecture and TG directly to the three broad material classes. Every polymer scientist must be able to distinguish instantly thermoplastic are linear or branched polymers. On heating, they softened, can be reshaped. This is a reversible physical process, which is exactly why thermoplastic can be recycled by remelting. Common examples are polythene, polypropylene, PVC, polystyrene, nylon. Thermostats. Thermostats are cross-linked networks. On heating, instead of melting, they char or decompose. An irreversible chemical process because you'll have to break covalent crosslinks, not just overcome intermolecular forces. This is why thermosets like bakelite, epoxy, and melamine cannot be recycled by remelting. Once cured, that shape is permanent. Elastomer sits in an interesting middle ground, lightly cross-linked coil chains with a glass transition well below room temperature. On heating, they soften only slightly and never flow because the cross links prevent permanent viscous deformation. Natural rubber, SBR, and neoprene are the classic examples. Here's a deeper physical insight. To remember, elastomer needs just enough cross-linking to prevent chains from permanently sliding past one another, but the chain themselves must remain highly flexible and mobile between those cross-link points. When you stretch rubber, you're reducing the conformational entropy of those coil chains. When you release it, entropy drives the chain back to their disordered coiled state. This is entropic elasticity, fundamentally different from the elasticity of a metal spring, which is enthalpic in origin. Next topic that we are going to discuss is mechanical behavior. Mechanical behavior, stress strain response. Let's now look at how polymers respond mechanically through the classic stress strain curve, one of the most information rich plots in material science. Notice the three distinct curve shapes here. The brittle material like polystyrene rises steeply and fractures at relatively low strain with plastic deformation. Beforehand, the plastic material like HDPE shows an initial steep rise followed by yielding substantial deformation before failure. In the elastomers, natural rubber shows a very different shape, low initial stress extending to very high strain, often with an upturn at high elongation as the chain becomes fully extended and start resisting further stretching. 5. Key parameter to extract from any stress strain curve. Young modulus E is the initial slope. It tells you stiffness. Yield stress marks the onset of permanent plastic deformation. Beyond this point, the material won't spring back. Tensile strength is the maximum stress the material sustains before failure. Elongation at break in the strain at the point of fracture. Your measure of ductility, and the toughness is the total area under curve, representing the total energy absorbed before failure, which is why a material can be high strength but low toughness, or vice versa, depending on how ductile it is. Next, we'll talk about the topic is natural rubber and vulcanization. Let's now look closely at rubber, a perfect case study connecting molecular structure, cross-linking, and mechanical behavior. Natural rubber is chemically cis-1,4 polyisoprene, harvested as latex from the Hebia barcellonesis tree in its raw form. Through rubber, though rubber is soft, sticky, and thermally unstable, not very useful as an engineering material, the transformation came in 1839 when Charles Goodyear discovered vulcanization, heating raw rubber with sulfur typically around 140 to 160 degrees Celsius along with accelerators zinc oxide. This process forms a mono di or polysulfide crosslinks shown here as the amber connection bridging adjacent polyisoprene chains, and the amount of sulfur used precisely control the final properties. Soft, flexible rubber, the kind in tires or rubber bands, uses only about 2 to 3% sulfur by weight, but push that up to 30 to 50% sulfur and you get ebonite or hard rubber, rigid, dense, and used in battery casing and certain insulators. The key takeaway: vulcanization converts a tacky, mechanical, weak material into a durable, elastic network with dramatically improved resistance to swelling, abrasion, and temperature change, simply by introducing a controlled number of covalent crosslinks between existing polymer chains. Next topic is characterization techniques. Let's now consolidate the analytical toolkit used to characterize polymers. This table is essentially a checklist you should be able to reproduce from memory. GPC GPC or gel permeation chromatography gives you the molecular weight distribution, Mn, Mw, and dispersity exactly as we discussed earlier. DSC, differential scanning calorimetry, measures heat flow as a function of temperature, and from a single scan you can extract the glass transition temperature, melting temperature, crystallization temperature, percent crystallinity, and the heat of fusion. TGA, thermogravimetric analysis, tracks mass loss with temperature, telling you about thermal stability, decomposition temperature, and even filler content in a composite XRD, X-ray diffraction probes crystalline order, giving you crystallinity index and despacing values. FTIR and NMR spectroscopy reveals chemical structure, functional groups, and tacticity and polymer copolymer composition. And DMA, dynamic mechanical analysis, measure modulus as a function of temperature or frequency, giving you storage modulus, loss modulus, the ratio tan delta, and yet another way to pin down Tg. Here's an exam tip worth remembering. A single d.sc trace showing all three thermal transition, a step at Tg, an exothermic peak at crystallization temperature Tc, and an endothermic peak at the melting temperature Tm is one of the most frequently tested interpretation. Question in GATE and CSIR net. Practice reading these heat flow curves until you can identify each transition instantly. The next topic is conducting and biodegradable polymers. Let's finish our tour of specialty, structure, property, relationship with two different classes of functional polymers. Conducting polymers rely on a conjugated backbone, alternating single and double bonds, which allows delocalization of pi electrons along the chain, similar to a principle to the delocalization you had studied in aromatic system. On its own, though a conjugated polymer is only weakly conducting, the real conducting comes from doping, oxidizing, and reducing the polymer to generate mobile charge carriers along the chain. Polyacetylene was the original discovery that earned a Nobel Prize. Polyaniline, polypropy- polypyrrole, and pedost PSS are more processable, widely used variants today, applied in OLEDs, organic solar cells, anti-static coatings, and the sensors. Biodegradable polymers take the opposite design philosophy. Instead of maximizing chemical stability, we deliberately build in hydrolyzed linkages, typically ester or amide bonds, that can be cleaved by water or the enzyme over the time, PLA, or polylactic acid, PHA, PCl, PGA are the most important example. The degradation rate can be tuned by adjusting crystallinity, molecular weight, and copolymers composition. A more crystalline, higher molecular weight polymer degrades more slowly, more slowly. These materials are essential in medical structures, controlled drug delivery system, and increasingly compositable packaging. So next, we are talking about and engineering polymers at a glance. This slide is more quick reference table, the kind of summary worth memorizing block by block, because these polymers monomer TG applications association shows up constantly across GATE, CSIR net, and journal chemistry interviews. Polyethylene, polyethylene from ethylene has a very low Tg, well below room temperature, which is exactly why it stays flexible even in cold condition. Used in packaging film bottles and pipes. Polypropylene from propylene has a Tg around -10, used in container and automotive parts. PVC from vinyl chloride has a Tg of 80, making it rigid at room temperature, and hence the need for a plasticizer we discussed earlier to make it flexible. Polystyrene has a Tg around 100, explaining its glassy brittle character at room temperature. PET made from ethylene glycol and terephthalic acid has a Tg of 70 and is a polymer behind both plastic bottles and polyester fiber. Nylon 66 has a Tg around 50 and you finds use in textiles, engineering, plastic and ropes. PTFE or Teflon, made from tetrafluoroethylene, is famous for its non-stick surface and chemical inertness, and PMMA or acrylic, made from methyl methacrylate, has excellent optical clarity used in lenses and display. Notice the pattern across this table. Tg correlates directly with room temperature behavior. Polymers with Tg well below room temperature behaves as flexible rubber, while those with Tg above room temperature behaves as rigid glass. That single number tells you an enormous amount about materials' everyday mechanical character. Slide 20. We are talking about key equation to remember. Let's now do a rapid fire recap of every equation from the module. Treat this slide as your final revision sheet before an exam. Degree of polymerization equals total molecular weight over, over repeat unit molecular weight. The Krathros equation x bar n equals 1 over minus 1 over 1 minus p for step growth polymerization and its modified form incorporating stoichiometric imbalance are the rate of radical polymerization proportional to monomer concentration and the square root of initiator concentration, kinetic chain length, connecting propagation and termination rates. The number average and the weight average molecular weight. Formulas remember Mn counts chains, Mw weighs them. Dispersity simply Mw over Mn and mark Hobing equation linking intrinsic viscosity to viscosity average molecular weight. Go through each of these, make sure you can drive where it comes from, not just recall it because postgraduate level exams frequently ask you to apply these equations to a numerical scenario, not just recite them. Thank you. That brings us to the end of this module on polymers. We have covered classification, polymerization mechanism, and the kinetics, molecular weight analysis, thermal and mechanical behavior, characterization, techniques, and specialty polymer classes, a genuinely comprehensive master level foundation. In the next session, we'll put this theory into practice with worked numerical problems on the Carothers equation and copolymer composition calculation. Exactly the kind questions you'll encounter in GATE and CSIR net lecture Arcadar Punjab. Thank you for learning with Camwald. See you in next lecture.